Okay, good evening to all and welcome to the another session of the NPTEL course Heat Transfer. So today is our week 2 session. So today we will be discussing about some of the questions related to the week 2 contents, which are the resistance in radial systems and heat generation in a plane wall and some extended surfaces, which in layman terms called as fits. Okay, so I hope you all have gone through the uh, week 2 contents. So it will be helpful for you to solve this question. So we will follow the previous week's style. So I will give you the question and I will give some time for you to solve. Then I will start solving the question. Okay. So only two persons are there. Okay. I hope others will join by the time. So let's get started with the first question. So this is a we have to find in this question we have to find out the critical thickness of insulation of a sphere. Okay. So I think you have already know this question answer. So and there are two critical thickness of insulation for a cylinder and a critical thickness of insulation for a sphere. So both uh, are, the, are there. It's a direct answer. If you know the answer, you can just comment in the chat box. What is the critical thickness of insulation for a cylinder? Why we are providing insulation? For example, we have a pipe that is steam is passed through. So we have to provide or we have to insulate the steam pipe. Why? What is the objective of insulation?
So to minimize the heat loss,
Yeah, to minimize the heat loss. So anybody know the answer for this?
no sir, can you tell it?
Yeah, yeah. So I do you know the critical thickness of insulation for a cylinder?
No sir, no. So
Yeah,
please provide it for those.
yeah. Actually, I will provide for the sphere the same way you can derive for the cylinder also. Okay. Obviously, in cylinder, it's already given in most of the heat transfer textbook. So we have a sphere. In this question, we are asked to find out the critical thickness of insulation for a sphere. Okay. First, I will draw a sphere of say radius R1, and I have a thickness. I am providing an insulation of say which is which is at a outer radius of R2. So the thickness of insulation is R2 minus R1. Okay. So we need to find out what is the critical thickness of insulation. So I am writing the insulation, the temperature at the insulated surface is let it be T2 and the inner surface let be T1. Okay. and we have a convection happening at with the ampere at which is at T infinity, and the at the convective transfer coefficient of H. So this is the situation. Okay. So what is the heat transfer? I already Q is equal to delta T divided by R total. Can you define what is R total?
Sir, 1 upon R1 minus 1 upon R2 by 4 by K plus H 1 upon H.
One more. I will write R2. This is for sphere. R2 minus R1 divided by 4 pi K R1 R2
Yes,
plus
sir.
1 by
1
H
by
times the
H.
outer surface.
Outer
That is
surface
4
area.
pi R2 square. Am I
R.
right?
Yes, sir.
Yeah. So so our objective is to minimize the heat loss, right? Our objective is to minimize the heat loss. So if we want to minimize the heat loss, we have to maximize or minimize R.
Yes, sir.
Means I'm asking a question. Our objective is to minimize heat loss. That is Q. We have to minimize the function Q. Okay. If we want to minimize the function Q, the function R should be, we should minimize the function R or maximize the function R.
Sir, maximize.
Yeah. So we have to maximize the function R. Okay. So I am taking the derivative of R total. So which is the variable here? R1 or R2?
Sir, R2.
Yeah. So we have to differentiate with respect to R2. So can you please say the answer? What is? So I am separating this 4 pi k R1 minus 1 by 4 pi k R2 plus 1 by h 4 pi R2 square. So we have to differentiate this function with respect to R2. Okay. So the first term is 0 because there is no function of R2. So if you differentiate the second term, you will get 1 by 4 pi R k R2 square minus 2 by h 4 pi R2 cube. Am I right?
Yes, sir.
Yeah. So we will equate this to 0 so that we will get the critical point. So if you equate this, you will get R2 should be equal to 2k by h. Are you getting this answer? When you cancel out the terms, this one got cancels, and R got cancelled. So yeah, you should get R2k by h. I hope you are
Yes, sir, we are
getting.
getting.
Yeah.
Yes, sir.
So this is the critical point, right? So now we have to differentiate once more to confirm whether this is a minimum or a maximum. Am I right? So once more we have to differentiate this, and if we differentiate once more, you will get minus 2 divided by 4 pi k R2 cube plus 6 divided by h4 pi R2 raised to 4. Am I right?
Yes, sir.
Yeah. Then you have to put this R2 means inside this value, right? Substituting R2 is equal to 2k by h in equation number 1. So can you substitute and say what is this value? Minus 2 divided by 4 pi k 2k by h the whole cube plus 6 divided by h 4 pi 2k by h raised to 4. I'm leaving this as a exercise to you. So if you do this exercise, you will get that this function will be always positive, will be greater than zero. Okay. So when the second differential is greater than zero, R total is minimum or maximum?
Sir, minimum.
R total is minimum, right?
R total.
Not the
Yes.
maximum.
Yes, sir.
So
Yes, sir.
here what we are getting is the R is minimum means the Q is maximum. So we at this R2 we are getting the maximum heat transfer, right? I hope
Yes,
you are
sir.
understanding. So there is no there is no not an optimum thickness doesn't exist. Here we have a critical thickness which is equal to 2K by H. So if you draw the curve, you will get something like this. This is Q, this is RC. So above this critical thickness, we have we can reduce the heat loss, and below this critical thickness, we have the heat transfer is increased, right? I hope you got this point. So this is the concept of critical thickness of insulation. So if we say, for example, uh, we are applying this to a sphere where we need to reduce the heat loss. So for that, we have to have a insulation which is greater than this 2K by H. I hope you got this point.
Sir, can you explain it one more time? Like,
No, actually, how we started. We started that for minimizing the heat loss, our total should be maximized, right?
yes, sir.
Then we found out this silent point 2K by H, and we found out
Yes,
that
sir.
when by the differentiate means by differentiating second differentiating, it is always greater than zero, which means R total is not maximized, it is minimum point. Okay. So at R2 or R is equal to 2K by H, the heat transfer is maximum. That is this point. Okay.
Yes, sir. Yes, sir. Yes,
So
sir.
if we increase this above RC, or if we add insulation above this, I means more than this R2 value, you will get a reduction in heat transfer. And if it is less than this one, you will get an increase in heat transfer. So if our objective is to reduce heat loss, we have to add an insulation above the R value, critical value. Okay. So in the same case, I have derived here for a sphere. The same method you can apply for a cylinder. For a cylinder, you will get K by H. Here it is 2K by H. That's the only difference. Okay. Let's move on to the next question. So here we have a base plate of 8 watts, 800 watts, household iron with a thickness of zero point 0.6 centimeter, base area of 160 centimeter square, and a thermal conductivity of 20. The inner surface of the base plate is subjected to a uniform heat flux by the resistant heater. At steady state conditions, the outer surface temperature is 85, so that is given. So, and we can neglect the heat losses and internal heat generation. We have to find out what is the temperature distribution inside the plate. Okay, so you may please try this. I think you can solve this. It's a question similar to the week one question. So what is the heat flux? Heat flux is 800 divided by the area, right? 800 watts divided by area is given 160 into 10 raised to minus 4 meter square. So you will get as 5 into 10 raised to 4 watt per meter square. Are you getting this value?
Yes, sir.
Yeah. So now it's like just we have to use our general heat conduction equation. So it's a one-dimensional heat conduction. There is no internal heat generation. So I'm taking this axis as x. Okay. So it's a steady state. So only the first term remains. Like that is d square t divided by dx square should be equal to 0. So the temperature profile, what is the temperature profile? The temperature profile will be a linear temperature profile. So it's say A plus B, X plus B. Okay. So now it's just we have to apply the boundary conditions like at X is equal to 0.006. Sorry. Yeah. Yeah. 0.006 meters, right? T is equal to 85 degrees Celsius. So 85 is equal to A times 0.006 plus B. This is the this is one equation. And second, at x is equal to 0, there we have a heat flux condition, right? Minus k dou t by dou x or dt by dx at x is equal to 0 is equal to 5 into 10 raised to 4. Okay, so can you get the now it's just simple mathematics. So can you get the answers? Final answer. What is dt by dx? It is a. So minus 20 into a should be equal to 5 into 10 raised to 4. So what is A? A will be minus 2500. Are you getting this answer?
Yes, sir.
Yeah. Now you can find out the B. B value will get as if you do 85. Sorry. What is B value? It will be 85 minus
Sir, 100, I guess. It should be 100.
which one?
B value.
B value is 100. Okay. Now we can just simply write T is equal to A is minus 2500 x plus 100. So you just cross check whether at x is equal to 0.006 meters you are getting T as 85 degrees Celsius. I will also cross check. And your temperature profile is right. Yeah.
Oh, yes, sir, we are getting it.
So this is our temperature profile. I hope you got how to solve this.
Sir, can you show the question, please, one more time?
Now here if you do some rearrangement you will get this in the form. Okay. So this is
Okay,
the
sir. Okay.
basic form. If you can do some rearrangement to match with the options. Okay. So let's move on to the next question. This question we have a steel cable having a diameter of 0.005 meter and an electrical resistance of 6 into 10 raised to minus 4 millimeter, carries an electrical current of 700 amps. The surrounding temperature of the cable is 30 degrees Celsius, and the effective coefficient associated with heat loss by convection and radiation between the cable and the environment is approximated to be 25. If the cable is uncoated, what is its surface temperature? Anyone got the answer? How we will do this? The whatever heat is generated, it should be given out.
So it should be equal to Q. I square R equal to Q.
Yeah, yeah. So if we equate that, you will get the surface temperature.
Yes, sir.
Yeah. So what is the answer?
So doing this.
Yeah, yeah. So what is the heat that is generated per unit length? That is Q triple prime per L. It is equal to I square R, right? Because why I am writing per unit length, because the resistance is given per unit length. So I square, what is 700 square into 6 into 10 raised to minus 4. So what is this answer? I think it should be around 294 watts per meter. Am I right? Are you getting this? Okay, so
Yes, sir.
this,
Yes. Yes,
yeah,
sir.
yeah. So this should be the heat that is convected. Okay, it's like here it is mentioned that it's an effect coefficient that takes care of both convection and radiation. Okay, so I'm writing this as HCR. should be equal to, it's already given 25 watts per meter square Kelvin. Okay. So this 294 should be equal to HCR times the, what is the area?
Sir, pi d square by 4.
No, where from where the heat transfer is taking place. Heat transfer area.
Ideal.
It's, yeah, pi TL. So here we, as we are taking per unit length, so the we can, we can, there is no need of L, or you can assume that we are taking for a 1 meter 1 meter cable. Okay, so it's pi into d into t surface minus t infinity. Okay, so it's 294 into is equal to 25 into pi into d is already given 005 times ts is what we need to find out. T infinity is how much? 30. So what is ts?
Sir, it is coming out to be 3024.
3024. Can you please cross check your answer? Because I am getting some 779. Anybody else got this answer?
Yes, sir. 779.
Okay. So the surface,
779 exactly, sir.
yeah. So the surface temperature is 779 degrees Celsius. So now this is a simple question. So we will go to the next question, which is a continuation of this question. Okay. Now we
Excuse
have
me,
a,
sir.
yeah,
Excuse me, sir. In
yeah,
this problem, we should not be dealing it with the problem of heat generation Q dot Q, Q per unit volume.
yeah,
So then how then we will proceed when if we are dou square dou square x by dou t square, then how we can do this? Because it is a problem of heat generation, I think, that Q dot.
yeah. So what is your doubt?
That del square t plus Q dot equal to 0. That we should not we proceed with this?
Are you means referring to that governing equation?
Yeah.
Here that is, it's not required, right? Here we are not interested in the temperature profile. If you
Okay,
are
sir.
asked to find out the temperature profile, you can use that formula.
Okay.
Here it's just a simple heat balance. Whatever heat that is generated, it should be conducted out at steady state. Okay. So that is our concept here. So we are just equating whatever heat generated should be the heat convected. It's not here. It's not a simple convection. It's already given. It's a convection convect radiation. So it should be taken out. Okay.
Okay, sir.
So here we have a very thin small coating of electrical insulation is applied with a contact resistance which is given. So at this point, when we have a very thin coating of electrical insulation, what is the surface temperature of the cable? It's a continuation of the previous one. The question number 3 was there is no insulation at all. Now we have a very thin coating of electrical insulation with a contact resistance of 0.02 meter square Kelvin per watt. So now what is the surface temperature? So here we have a electrical coating. So let's write the uh, resistance network. So the temperature of the cable I am denoting it as Ts, and between this and the coating we have a contact resistance of Rc divided by pi di into L. Then we have a Ti, then we have a convection resistance of T infinity, that is 1 by H into pi Ti into L. As we already mentioned that it's a very thin coating, we are neglecting the thickness. Okay. So now I think you can solve because RC is already given. Just we already know what is Q dot. So L I'm writing. So either you can take L is equal to 1 and solve the question. So Q dot is equal, I'm taking L is 1 meter. So the heat generated should be equal to Ts minus T infinity divided by 1 by pi Ti Rc plus 1 by H. So this is already known. What is how much? 294. 294 should be equal to Ts minus T infinity is 30. 1 by pi Ti is how much? Ti Rc is given as 0.02, right?
Excuse me, sir.
0.02
That
plus 1 by.
RC should be directly added, no? It should not be divided by area.
No, you check the unit of Rc. It's given per unit area. Yeah, if it was simply K by watt, you can, yeah, there is no need of dividing by area.
Okay.
Okay. So you should check the units also in some cases.
Okay, sir.
Yeah. By H is how much? HCR 25. Okay. So you will get what is
So,
Q.
so
Yeah.
1153.
Yeah, it's 1153 degrees Celsius. So next question is also a continuation of this question. Okay. What should be the thickness of this insulation which will yield the lowest value of cable temperature? So what do you expect from this means which yield the lowest value of cable temperature? When the cable temperature attains lowest value,
The critical resistance.
yeah, at critical radius, what happens? I already told. When the heat transfer is increased or when the heat transfer rate is maximum, we will expect the minimum temperature. Like I think nobody doesn't have any confusion with that. When the heat transfer rate is increased, obviously the temperature will decrease. Am I right? For example, if you have a cup of tea, right? Okay. And if you are just simply keeping it, the temperature will be means hot tea. I'm mentioning. It is the heat is transferred by natural convection only. So the temperature will be higher. So if what we do is uh, we will blow some air, right? So we are changing the mode of heat transfer from natural convection to forced convection, which increases the heat transfer. So the temperature of the fluid will get reduced faster. Okay, like that. At critical, what is this is a uh, cylinder. So the critical radius of insulation is K by H,
H. Yes.
right? So K is already given how much? 0.5. H is given 25. So this is 0.02 meter. So what is the critical radius of insulation? Here, this is the critical radius of insulation. You should be very careful. This is the critical radius of insulation. But in the question, it is asked the thickness of insulation. It's not the critical radius of insulation. Okay. This is how the some gate questions can happen. So you are asked to find out the thickness of insulation, and you first find out the critical radius of insulation, and this answer, that is 0.02 meter, will be exactly there in the option. So most of the students will give that option, but that will be wrong. Whether the thickness of insulation and this RCR, whether it is same or different.
So it should be different.
Yeah. So we have to minus from the base R, right? So the thickness is RCR minus the actual radius of the steel cable, right? This is 0.02 minus what is the its diameter is given 0.005. What is this answer?
So D, 0.0175.
Yeah. So you should be very careful with the question what is asked. Okay. So now can you find out what is the surface temperature at this case? Means when there is a contact resistance, and also we have we have an other thickness of other insulation with this uh, with thermal conductivity 0.05, which is at critical radius of which has a thickness of this 0.0175, and also some convection happening. So can you find out what is the surface temperature of the cable under these conditions? So what will be the total resistance? R will be, we have a contact resistance already, RC divided by pi di, right? Or d1, I can write di, plus we have a resistance due to this insulation thickness, that is ln RCR divided by R1, or DCR divided by DI or RI divided by 2 pi k. I am writing in terms of per unit length, or plus 1 divided by HCR pi D. Whether now it's pi DI or DCR.
So DCR.
Yeah, because now now the insulation has added up to the steel cable, and now the heat transfer is happening from the DCR, from the surface of the insulation. Okay. Now I'm just giving this as an exercise to you, so you can find out what is the. It's because everything is given. That is RC is given by DI. What is DI? It's already given 0.005 meter. RCR is given. It's already 0.0175. Sorry. How much? 0.0. If anybody calculates, you can, by this time, you can say 0.02 meter. And Ri, which is d by 2, di by 2, which is 0.0025 meter, and dcr, it is 2 times r, that is 0.04 meter. So now you can find out by r is equal to how much, t surface minus t infinity divided by r total, sorry, this is 294. So you can find out what is t surface. So you please cross check whether you are getting some answer like 692.8 degrees Celsius, almost close to this answer. Okay, this I am giving this as a homework to you. You can just cross check whether you're getting this answer. Okay, now let's move on to the next question. Here we have a metal rod of 2L. Okay, first I will explain the question, then I will give you some time to solve. We have a metal rod of 2L with a diameter d and thermal conductivity K is inserted into a perfectly insulated wall, exposing half of its length to airstream with a which is flowing at which is at a temperature of T infinity, and a convection coefficient at surface of the rod. So we have a metal rod of length 2L. Half of its length is exposed to air, while the half of the other half is means what to say, is inserted into a well insulated wall. Okay, an electromagnetic field induces volumetric heat generation at a rate of q dot within the embedded portion of the rod, which means there is a heat generation inside the portion which is inserted into the well insulated wall. Okay, so what is the base temperature of the rod which is half exposed? So we have the other half is exposed to ambient or air. So what is the base temperature of the rod which is half exposed? Which means what is the temperature? I hope you understand what is meant by the base temperature. So the exposed half, right? So it is going into the insulated wall. So what is the temperature at that area? Okay, and you can assume the exposed region as a infinitely long fin. So any doubt in this question? Yes.
Yes, sir. How will we proceed?
Yeah, actually, what is this? I will draw the schematic, then I will proceed. Say this is the rod, okay, of length 2L. So I am dividing it into L, half portion L and half portion L. So it is given that half portion is inserted in a well insulated wall. Okay, so this much portion is inside this well insulated wall, and this is exposed to air at T infinity and H. Okay, so we are asked to find out this temperature, is TB. Okay, and it is already means stated that there is a uniform heat generation. This is happening within this portion, which is inside the insulated wall, and we can assume this as a infinitely long fin this portion, that is the exposed portion, we can assume it as an infinitely long fin. Okay, I hope this much it's clear. So we are asked to find out what is TB. Any idea how to proceed?
Sir, first of all, we can find the Q value, I guess,
Yeah,
for the unexposed region, like
yeah,
the
where the
half
heat
length.
generation is happening. Yes,
Yes, sir.
yeah, yeah. That so
Uh,
yeah, from there only we start. So it's mentioned that it's a perfectly insulated wall. So whatever heat that is generated within this portion, that is within the left side portion, it can only be transferred through the fin. Is that clear? Because every side is insulated, it can only cross through this portion. Is that clear?
yes, sir.
Yeah. So we already got the what is the Q for a fin. Now just use the fin equation for an infinitely long fin. I hope the question is clear. What is the Q fin for an infinitely long fin? That is rho HPKA TB
Into
minus T
minus
infinity.
T infinity.
Is that right? So
Yes, sir.
yeah. So now the it's almost done with the answer question. We are already, it's given what the heat generation rate is already given. Okay, so it's per unit volume. So it's all you know how much volume is inside the, in how much volume the heat generation is happening. So you have to multiply by the volume of volume of the road. Okay, and H P K everything is known to you. So you just need to substitute. So what is the heat, the total heat generation Q naught into area of cross section into how much portion is in how much portion the heat generation are happening, or L.
Sir, L length, L
L length
length.
is equal to root HPKA TB minus T infinity. So TB is equal to T infinity plus Q dot ACL divided by root HPKAC. Is this right? Or T infinity plus Q dot L root of AC divided by HPK. So already all the values are known to you. That is Q dot is how much? 10 raised to 6 watt per meter cube. L is already given 50 mm. So 0.05 meter. Area of cross section is pi by 4 into d square. That is diameter 5 mm. So 5 into 10 raised to minus 3 the whole square. So H is given 100 watt per meter square Kelvin. Then perimeter, what is perimeter? Pi d. Pi into 5 into 10 raised to minus 3. K is already given 25 watt per meter Kelvin. So what is TB? Can you please calculate?
Or is it 90.7? Oh, sorry, sir. 55.35. Sir, you have muted your mic.
So, yeah, are you getting this answer? Sorry.
Yes, sir.
Okay, fine. So let's move on to the next question. So this is also a question that is related to fin. We have a copper rod of diameter 1 of diameter d and length l. It's mentioned are used to enhance heat transfer from a surface that is maintained at 100 degrees Celsius. Okay. One of the rod is attached to this surface while the other end is joined to the second surface maintained at 0 degrees Celsius. I hope you can visualize. Okay. We have one copper rod where one surface is one end is attached to a surface maintained at 100 degrees Celsius, and another rod which is another side, opposite side of the rod is attached to a surface which is at 0 degrees Celsius. And air at 0 degrees Celsius is flowing between the surfaces, which means over the rod, with a convection coefficient of 100 watt per meter per Kelvin. So, what is the rate of heat transfer by convection from the rod to air? Is the question clear?
Yes, sir.
Yeah. So you can start solving this. Okay, first we will write what is the governing equation for this problem. This is a simple fin problem. So in fin, what we have done is we have the governing equation for the fin, and the we have uh, substituted the different boundary conditions according to the different cases for fin, like insulated fin, infinitely long fin, fin with tip convection, etc. So here we will just start from the basic equation. So this will help you to understand also. So I'm taking a small element dx. So qx plus dx and some convection q convection. Okay. So by energy balance, q dot in minus q dot out should be equal to 0. It's a steady state. So we have qx is equal to qx plus dx plus h times p dx into t minus t infinity. So dqx divided by dx plus hp t minus t infinity should be equal to 0. So we write qx is equal to minus ka dt by dx. So, and I'm writing theta is equal to t minus t infinity. So I will get the final equation as d square theta divided by dx square minus hp by ka times theta is equal to 0. So this, I have not written anything new. This is just the fin equation. Okay, it's already derived in the class. Now, what is different is what we have to do is we have the two boundary conditions. Accordingly, we have to put to the solution. What is the solution for this equation? Theta is equal to c1 e raised to mx plus c2 e raised to minus mx. Is this right?
Yes, sir.
Yeah. Now, there is we have to just substitute the boundary conditions. That first boundary condition, what at x is equal to 0, what is theta? It is t minus t infinity, which is equal to 100 minus 0, which is 100. Okay, so 100 is equal to c1 plus c2. This is equation number 1. Okay, now at x is equal to L, which is equal to 0.025, we have theta is equal to t minus t infinity is equal to 0. 100 minus 0, 0 minus 0. So you will get 0 is equal to c1 e raised to m times 0.025 plus c2 e raised to minus m times 0.025. What is m? It is root hp by ka, which is equal to h is 100. That is perimeter pi d. So pi times d is how much? D is 1. Sorry. Yeah. 1 into how much is d? 1 mm. Okay. 1 into 10 raised to minus 3 divided by k is 400 into area is pi by 4 into d square. So you will get m value as approximately, I think, 31. So you may please check. We can cancel this out, and you can finally you will get 100 into 4 divided by 400 into 10 raised to minus 3. Can you find out what is this value m?
So 31.62.
Yeah. Okay. So now you just substitute here, that is exponential. If you substitute e raised to this 31.62 into 0.0265, so and and the negative exponential value also, you will get the equation as this is equation number 3. So you can solve 1 and 3, right? It's a set of linear equations, and we will get the values of C1 and C2. So I'm directly writing, you can try later. These are the values of C1 and C2. So the temperature distribution is minus 25.94 e raised to 31.62x plus 125.94 e raised to minus 31.62x. Okay. Now we got the temperature distribution. So the heat will get transferred from here to here, right? It is from high temperature to lower temperature. So a part of heat will enter this side, this from the left surface of the rod, and a part of heat will go to the or leaves from the disk, or we can say some amount of heat is conducted into the rod through left side, and some amount of heat is conducted through the rod from the right side, plus some amount is conducted out. Is that clear?
Yes, sir.
Yeah.
So will you please show the full statement, please?
What
Statement of the question, sir.
statement?
Yeah. Okay.
Yeah. So if we find out what is the Q convection here and Q convection here, and if you subtract that, you will get the what is the convected from the rod. Am I right?
But sir, you are saying convection. I think you should say conduction. Am I right?
I told conduction, right? Some amount of heat is conducted, some amount of heat is coming to the rod by conduction through the left side. Is that correct?
Yes, sir.
And some amount of heat is going from the rod through conduction to the 0 degree block at the right side. That is also right. And some amount is convected to the air.
Yes.
I hope you got that. So if we find out that is Q conducted at x is equal to 0, which is equal to minus Ka d theta by dx at x is equal to 0, that is minus 400 into pi by 4 into 0.001 the whole square into minus, and directly writing this, you can just cross check 1.478 watts. And Q conduction at x is equal to L, that is minus Ka d theta by dx at x is equal to L, will get minus 400 into pi by 4 into 0.001 the whole square minus 35. So the Q convection is equal to Q conduction at x is equal to 0 minus Q conduction at x is equal to L, which is 1.478 minus 1.104, which is around 0.373 watts. So the mathematics part you can later try. So I hope uh, the concept is clear how to do this problem. After that, it's just solving the differential equation and putting the boundary conditions. Okay. So let's move on to the next problem.
Excuse me, sir. In the previous
Yeah.
problem, that
Mm.
you have not used any equation for convection at
No,
Newton's law.
no, you can try in that way also. What I did is, you say, you think some amount of heat is entering through this by conduction. Okay. Some amount of heat is going from the rod through conduction plus convection. At steady state, this should be this Q C1 conduction 1 should be equal to Q convection plus Q conduction. So what I did is I find out these two and subtracted.
Okay. Okay.
So you can try this question. So a rectangular fin of length 30 centimeter and width 30 centimeter and length and width 30 centimeter and thickness 2 mm is attached to a surface at 300 degrees Celsius. The fin is made of aluminum and is exposed to air at 30 degrees Celsius. The fin end is uninsulated and can lose heat through its end also. The convection heat transfer coefficient between fin surface and the air is 15 watt per meter square Kelvin. Determine the fin temperature at the tip.
Excuse me, sir.
Mm.
Sir, in
Yes.
the previous problem, if we do it by convection, then I think these boundary conditions can be that conduction at x is equal to 0 and a conduction at x is equal to x equal to L. So these
Mm.
equations can be avoided if we are directly doing it with convection.
So can you please say how you can do by Newton's law? Because you may be thinking that the entire this road is at same temperature, right?
Yeah.
No, it's not. It's not true. The temperature is the temperature of the road is not uniform or not same. That's fin.
Okay.
That's the concept of fin.
Okay. Okay. Yes, sir. Yeah, I have understood, sir.
Yeah. Okay. So you cannot use the direct convection equation. The temperature is varying. It's like an exponential variation. That's what we already found out from theta. If you see the theta equation, it's an exponential function. So
Yes,
you
sir.
can only okay,
Yeah, sir.
yeah,
I
you can only
understood.
use the t minus t infinity if t is constant
Yes.
along the road. Okay, this question, it's also a fin question. So fin with insulated, sorry, fin with uh, and uninsulated, and the heat is convected from the tip. So if you see the textbook or if there is the equations for convection from the tip is very big and solving that is very laborious. So we can have a simple assumption here. Like what assumption? Does anybody know about that? We can convert this case into a pin with insulated tip by some adjustment. Means by having a corrected leg. Are you aware of that? It's an approximation. It's not the actual. But you will get an approximated answer, close to the answer. So what we are doing is here if this is a fin, okay, I'm taking a pin fin, and here we have the convection happening. What we do is we will take this area and attach along the length of the fin. That is the corrected length. So this is the actual length. Okay, and we are adding this extra area along the length of the fin, so that whatever heat that is lost by this area will be accounted by this extra area added along the length. Okay, so hence we can assume this length as insulated. I hope this concept is clear to you.
So that assumption we are making of insulation, so only that curved surface area is insulated.
Yeah, insulated in the sense that the outer tip of the fin, this circular, if this is a pin fin, it will be a circular cross section, and if it is a straight normal fin, it will be a rectangular cross section of the tip of the fin. So normally there are basically three types of assumption for the fin. One is infinitely long fin, one is insulated tip, fin with insulated tip, another is uninsulated tip with convection happening. This is the question. This third case is the question here. So if you see the means equation for the last case, it is very complex equation. So in order to get rid of that, we are having a approximation here. Okay. So now I will just I'm not solving this question completely. I'm giving this as a homework to you. So for a pin fin or for a straight fin, the corrected length is L plus T by 2. T is the thickness of the rectangular fin. Okay. And for a pin fin, which pin fin means the pin with the circular cross section, the corrected length is L plus D by 4. Okay. So I hope you know this equation, that is theta by theta with the temperature distribution for a fin with insulated at the tip is cos HM LC minus X divided by cos HM LC. Okay. So now the LC you can find out, and you are asked to find out the temperature distribution at X is equal to LC. So this becomes cos H M 0 divided by cos H M LC. So you can find out this value by using the hyperbolic cos function, and also then you will get the theta value, and from that you can easily find out what is the temperature of the tip. I hope you will be able to solve this. So the answer will be I think it is 70.3. Okay, you can just cross check this. If you're not getting, I will solve in the next class, because I'm skipping this because we solved a similar kind of questions already. Only this portion is changed. So we will go to the another question. We have a uniform 8 uniform area fin of thickness 1.2 mm and length 35 mm are integrated to the base of a heat sink in an electronic cooling device application. The thermal conductivity of the material is 187, and all the exposed surfaces are convectively cooled by an ambient air at 22 degrees Celsius, subject to a heat transfer coefficient of 16.5 watt per meter square Kelvin. The base temperature has been measured as 64 degrees Celsius. Determine the overall surface efficiency or the overall efficiency of the fin. This is the question. This I will just start this because we have a base, okay, and we have 8 fins arranged like that. It is arranged, okay. This is the heat sink, and this is the fin. So I am taking the thickness of the twin fin as 2t, okay. I'm using 2t because in some textbooks it is mentioned as 2t. So if you refer in the future, so that you won't get confused. So the thickness of the fin I am taking it as 2t, which is given as 1.2 mm, and the length L, it's given as 0.035 mm, sorry, 0.035 meter, and the number of fin n I'm taking, it is given as 8 fins, and the thermal conductivity of the fin is given as how much, 187 watt per meter Kelvin. At T infinity or T ambient, it is given as 22 degrees Celsius, and the heat transfer coefficient is given as 16.5 watt per meter square Kelvin. Okay, and the base temperature is measured. The base temperature is already given TB, which is 64 degrees Celsius. This base temperature. Okay, this is TB. Okay, so sorry, in this question some values are missing, so I will add this. I think I forgot to add this. So the fin spacing, that is a spacing between the fin, I'm taking it as S. Fin spacing S I'm taking, that is given as 0.004 meter. Okay, and the width of the fin, that is width means into the width of the fin array is into the plane of the paper, right? You cannot see that. So W fin array width, it is given as 0.098 meter. I think, yeah, now the all the values are given. We have to find out the overall efficiency of the fin. Overall efficiency. Okay. So for that, I will just solve this. Okay. So what is the overall efficiency of the fin? That is the Qt divided
QF
by
upon
Qmax,
Qmax.
right? Yeah. So we have to find out what is the total heat transfer divided by the maximum heat transfer. So I'm defining some areas, that is AT, area total exposed area, including fin. AF, total area of fin, just fins. Okay, that is the AE, that is AT minus AF, that is the exposed parent area. Means after we have a heat sink, and after placing the fins, there will be some exposed areas on the heat sink. That is the exposed parental area or the exposed heat sink area. So the what is the heat transfer due to exposed area, that is QE. What is QE? H, heat transfer coefficient, times area of the exposed area into theta b, means the T surface minus T infinity. Okay, because the heat sink surface is at constant temperature. Am I right?
Yes, sir.
Yeah. Now, next part is we have to find out heat transfer from fin. That is Q fin. Q fin is area of fin H, or H area of fin times theta b. This is not the heat transfer from the fin. What is this? This is the heat transfer from the fin when the entire fin is at the same temperature, right? But in actual fin, the temperature of entire the along the length of the fin, the temperature is not constant; it's varying. So, into the efficiency of a single fin. I hope this is clear to you. And just rewrited the efficiency of a fin. Efficiency, what is efficiency of the fin? Q fin divided by the Q max. Maximum heat transfer happens when the entire fin body is at the same temperature. Are you agreeing with me?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So you got this. So we have to find out the total heat transfer, which is QE plus QF, which is AE H theta B plus AF H theta B into theta, which I can write AT minus AF to H times theta B plus AF H theta B eta. Okay, so Q total is equal to AT times H theta B 1 minus AF divided by AT into 1 minus eta. Can you please check whether you are getting this? Because I taken ATH theta B as common. And you please check whether you are getting this expression. AF divided by AT. Are you getting this expression?
Yes, sir.
Yeah. So we got QT. So what is the overall efficiency? QT divided by Q max. So what is Q max? Q max happens when both the base, the fins all are at same temperature. That is represented by this value. Am I right? It is area total H times theta B. So I'm just bringing this down so that I will get QT divided by Q max. So the efficiency becomes A1 minus AF divided by AT into 1 minus eta. This is the overall efficiency of the fin array. Okay. Now it's just we have to substitute the values. So you can start substituting the values. So I have
Sir,
some space constraint here.
sir, is the efficiency of the fin is given?
Efficiency of the fin you have to find out. Tan H ml by ml. You can assume it as an insulated fin. Okay. tan h ml divided by ml. Its overall efficiency is equal to 1 minus AF divided by AT, 1 minus eta. So what is the efficiency of the fin? Tan h ml divided by ml. What is m? Root hp by ka. Okay, so if you write this, you will get 12.2. Anybody getting this m value?
Excuse me, sir.
Yeah,
What will be P when the fin is rectangular?
p. P it
Yeah,
should be how what is the perimeter for a rectangle? 2 times
12
length
plus
into breadth,
3.
right?
Pardon?
2 times length plus breadth. Here it will be 2 times the thickness, that is 2t, plus what the width, that is into the plane of the paper. Okay, so you can calculate this, you may get the answer as 12.2. So now you can find out the efficiency of a single fin as tan h ml by ml, which will get us, you have to calculate the tan h value, that is you will get 0.4028 divided by 0.427, you may get as 0.9433. Okay, now just you need to find out what is the area of the fin, that is perimeter of fin, perimeter of fin times the length into the number of fins. Okay, this is 2 into what is perimeter, 2t. 2t means, or the thickness is given as 0.0012 plus 0.098 into length of the fin. So this is also given into 8. 8 is the number of fins, which is 0.0555 meter square. You'll get something like this. So total area is the area of the fin plus the parental area, means the exposed area of the heat sink. That is how much the space is, spacing times the length or the width, that is S into W times n minus 1. Okay, I hope how you got n minus 1. So say for example, if there are 3 fins, so how this area is 2, is n minus 1. So if it is 4, this area exposed heat sink area is 3. So what how much fin is there? Minus 1 will be the exposed area. This is how the exposed area of the heat sink will get it as S spacing W n minus 1. Okay, you will get this answer as around 0.0582 meter square. So can you please substitute in this equation and tell what is the overall efficiency? Because everything I calculated, I just need the uh, final answer, that is 1 minus AF is already given 80 into 1 minus efficiency. Can you please calculate and say?
Sir, is it 94.59%?
How much? How much? Can you please repeat?
Sir, 94.59%.
Yeah. It's almost 90. Yeah, it's 94 point almost 6.
94.3, sir. 94.3.
Yeah, it's almost close to 94.
Yeah.
Okay. So the overall efficiencies will get us around 94 percentage. So this is how you calculate. This is a array of fin questions. So this kind of questions you can expect in your like normal semester examinations. Okay. So I will just solve this question. Okay, for you. I hope that the previous question was clear. Is that clear?
Yes, sir.
Yeah. Okay, I think yeah, one more question is left. So we need to find out the effectiveness of the fin. Earlier we found out the now this I won't solve completely. I will just give you the formulas. You can solve it in the next class and come in the next class. So here in this question, we need to find out the effectiveness of the fin. So what is effectiveness of the fin? Q total divided by
Qmax.
that is efficiency, right? Yeah, okay, fine. Q max. Effectiveness means Q fin by Q without fin, right? That is Q max is efficiency. Effective. How we will say define the effectiveness of the fin? We have a surface, right? In this case, say for example, we have a heat sink. So by adding the fin, how much the heat transfer increase? That is the effectiveness of the fin. Am I right?
Yes, sir.
Yeah. So our effectiveness is Q total. Q total means the total heat transfer from the fin plus the exposed base area divided by when there is no fin at all. That is the exposed, there is no means when the entire heat sink area into H into theta B. I hope you got that. What is fin? Fin effectiveness is Q fin by Q without fin. That is, I will write Q total. We already found out HE, AE, HE theta. Sorry, there is no HE. H theta B plus AF H theta B times eta divided by AP H theta B. Or we can write AE plus AF eta divided by AP. AE, AF we already found out. So the only thing we need to find out is AP, that is area of the fin. Sorry, the area of the heat sink. I hope this much
Sir,
it is
what is
clear.
AP? What
A,
is AP, sir?
AP is the area of the heat sink. When it's the total area of the heat sink. You imagine the heat sink without any fins. Okay. So imagine like this. Initially we have a heat sink. Okay. On top of that, we are placing fins. Am I right? So if we are removing the fins, we only have the heat sink area. So the entire heat sink area. I hope you got that. What is AP? Or we can, sorry, it may be confusing for you. I am writing heat AH. Okay, now is it clear?
Yes, sir.
Yeah. So I hope you will be able to calculate this. So I am giving this as a homework to you. Okay. In the next class, I think the answer is around 14.78. You can cross check with the answer. So the only thing here is to find out AH, because everything we found AE, AF, efficiency, everything we find out in the last class, or sorry, in the last problem. So the only one left is this one, which AP, sorry, AH. So that is just, you just imagine the geometry, you will be able to solve this.
Okay, sir.
Okay. So should I discuss this also, or we will try and come next class?
Sir, we'll try it.
Okay. Okay, then we will stop our session here. So thanks for joining the session. I hope this session was helpful for you and you learned something new. Okay, I expect your participation in the next class also. Thank you, and have a nice week ahead. I'll see you next Monday. Thank you all.
Thank you, sir.